Hello everyone, welcome to my channel Mondays Learning Hub. So as you know, we have been covering the second part of the course Kinematics of Machines. The topic which we have picked up first for explanation is velocity analysis and mechanisms using graphical vector approach. We will start with the velocity analysis of a simple 4-bar mechanism. So I will divide this velocity analysis problem into two parts. The first part is which data is available with us, or you can say which data will be provided to us, and the second part is what parameters we need to calculate. So let us just see the example of a 4-bar mechanism. So usually in velocity analysis problems, the configuration diagram of the mechanism is provided. When I say the configuration diagram of the mechanism, that simply indicates that the length of the links in the mechanism, it will be given to us. So let me just write it down here. So first thing which is given to us is length. Now at the same time, the angular velocity of one of the links, right, which is usually the input link, it will be provided to us. So lengths of links, and then angular velocity of input link. So as you can see here, the angular velocity of the input link, it is provided as omega, and this input link AB, it is rotating in a clockwise direction. Now this is the first part of the problem. That means here we can see the data which is available with us. So we can see the configuration diagram, that is the length of the links. That means you can say the length of link AB, BC, CD, AD, and also the dimensions of BF and CF, they are provided to us. At the same time, the angles, you can say the angles which each of the link is making relative to other, that is also given to us, right? So all these angles, right, and all these dimensions, they are provided to us. So usually this is the data, right, which is given to us. Now let's see what we actually need to calculate. So obviously what we need to calculate is the absolute velocity of the joints, right? Let's say this joint C, and then you can say the absolute velocity of any intermediate point, right? For example, here you can say that this E is an intermediate point on this length BC. So absolute velocity of point E, and then finally the absolute velocity of point F. So obviously the parameters which we need to calculate are simply the velocity parameters of the points on different links in the mechanism, right? So now why I'm not talking about the absolute velocity of point B, that I will tell you later on, right? So parameters which we need to calculate, correct? Now at the same time, besides the velocities, the linear velocities, we also need to calculate the angular velocities of link BC and CD, right? So now let's move ahead and let's see the process for computing these velocities using graphical vector approach. Now here we will try to understand the process first, right, and later on we will assume certain numerical values for the link lengths and also these angles, and at the same time this angular velocity, to compute the actual velocities of this point C, E and F, right? But right now let's first try to understand the process. Now first we will talk about velocity of point C relative to A, right? So let us take this first one, that is to calculate the velocity of point C relative to point A, right? Now when I say velocity of point C relative to A, that simply means absolute velocity of point C. So why I am saying that this is the absolute velocity of point C? Because we know the point A in this mechanism is a fixed point, correct? So now let's move ahead. So let's see the first step. So the first step is simply to write the vector equations for point C, right? Now just observe carefully. I am saying here, write down the vector equation for point C. Similarly, if you are interested in calculating the absolute velocity of any other joint, let's say joint B, right? So you will write down the vector equation, maybe you can say for joint B. Or let's say if you are interested in calculating the absolute velocity of this point E, so you will write down the vector equation for point E. And similarly you can do the same thing, repeat the same thing for this point F, right? But here let's see, the first step is to write down the vector equation for point C. So the vector equation for point C, it is simply given by VCA vector equal to VCB vector plus VBA vector. Now let us see what is this vector equation, right? So if you remember the triangle law of addition of vectors, from there you can easily conclude that the velocity of point C relative to A is nothing. It is simply equal to the velocity of point C relative to B plus the velocity of point B relative to point A, right? So now you have to remember that what we are going to do, we are simply following the order CBA in order to write down the vector equation for point C. And now afterwards, if you see this, that usually, right, if you write down this thing, the same thing in the vector diagram format, so you can write down these vectors as AC vector is equal to BC vector plus AB vector. So just remember, don't get confused into the equations here, right? When you write down simply this thing into the velocity vector format, then what happens? The letter C, it will come before A, right? But if you write this thing in the vector diagram format, so obviously the letter A, it will come before the letter C. And the same applies to VCB vector and VBA vector. So this thing will become more clear when we will start drawing the vector diagram. Now let's move ahead and let's see what is the next step. Now if you observe carefully, in this entire mechanism there are basically two fixed points. So one fixed point is A, another fixed point is D, correct? So what you can do, you can also say that absolute velocity of point C, right, this will be simply equal to VCA vector, and this vector, it should be equal to VCD vector. So now what we are going to do, we will simply rewrite this equation, and now the new equation, it will become VCD vector is equal to VBA vector plus VCB vector, right? Now again in the vector diagram format, this will become DC vector, right? DC vector is equal to AB vector plus BC vector. Just remember, you have to interchange the letters here, that's it, right? So then you can move from the velocity vector format to the vector diagram format, right? Now from here, if you observe, the equation for the velocity vector of point C is complete. Now let us move to the second step. Now here I am going to quickly tell you, right, a very important trick, and this trick will help you to solve this problem in a very easy manner, right? So you don't need to actually memorize each and every point, right? So you just remember this trick, and the other steps of this velocity analysis problem, they will come automatically to your mind, right? So let us see what are those tricks. So the trick is to simply run a magnitude and direction analysis, right? So now what is this magnitude and direction analysis? Let us quickly see that. So what I am going to do, I will quickly draw a table, right? So once you become habitual, right, so there is no need to actually implement this trick again and again. But initially when you are a beginner, I would suggest that you follow this trick quickly, right? So now, so let me just prepare a table. So this is vector, then let me write down another column. So this column will represent the magnitude, then let me write down another column. This column is going to represent the direction, right? So now let us see that what is this magnitude and direction analysis. Now we will move to our vector equation, right, and then we are going to check each of the vector one by one, right? So let us see that. So we will start first with VCD vector, right? So now we will check whether VCD vector is known in magnitude only or direction only or it is known in both magnitude and direction, right? So let's observe that. So VCD vector, if you see that the magnitude of VCD vector is right now not known to us. In fact, that is our objective here, to calculate the absolute velocity of point C. Now let's talk about direction. So if you carefully observe, the direction of VCD vector in partial sense is known to us. So why I'm saying in partial sense? So usually we know that the linear velocity of point C with respect to D, it will be perpendicular to DC, correct? So why I am saying in partial sense? Because right now we know that VCD vector will be perpendicular to DC, but still we don't know the sense of this direction, right? That means whether this vector, it is going to point towards left or towards right, right? So this thing is still unknown to us. But now let's go to the next vector, right? So the next vector is VBA vector, correct? Now VBA vector, if you observe carefully, right, it is known in magnitude as well as direction. Now here comes the trick, right? Initially I mentioned that here, when I mentioned the parameters which we need to calculate, so for some time I just skipped this velocity of point B, right? So that is the reason. Now you can observe the reason here. So we usually know that once the angular velocity of this link AB is known, right, then it is possible to calculate the velocity of point B relative to A from the given data, right? So that's why we skipped that factor here. So now you can see easily here that VBA vector is nothing. VBA vector is simply equal to AB multiplied by omega. So from here you can calculate the magnitude of VBA vector. Now let's come to direction. So obviously the direction is known in complete sense here, right? So when I say complete sense, so we know that VBA vector, it will be simply perpendicular to AB, and also we know that this VBA vector, it is obviously going to point towards the right direction, right? So here you can see that this link AB, it is rotating in clockwise direction, and that's why this VBA vector, it will point towards the right, right? So let me just draw the sense here. So sense, I will show it with arrow, something like this. That means it simply indicates that it is pointing towards the right direction. Now let's quickly move to this VCB vector. Now let's check that whether VCB vector is known in magnitude or direction, right? So you can again say that VCB vector, that is velocity of point C relative to B, it is not known in magnitude, right? But now let's check the direction. So obviously in partial sense this is known to us that VCB vector will be perpendicular to BC. But again we don't know that whether with this VCB vector it will point towards up direction or down direction. This thing is still not known to us. But partially we know that VCB vector will be perpendicular to BC. Now once we have run this, right, magnitude and direction analysis, now I am going to mention a very important statement here. So just focus on that statement, right? So if you observe your triangle law of addition very carefully, then you can conclude that if two vectors are there, which are known in direction only, then it is possible to calculate their magnitudes. So this rule we will apply, right, while drawing the vector diagram to find out the magnitudes of two vectors which are known in direction only, right? So now let's see here, if you observe carefully this vector table, right, so we can see here that here these two vectors, that is VCD vector and VCB vector, they are known in directions only, right? We only know the direction, that VCD vector will be perpendicular to DC and VCB vector will be perpendicular to BC, but we don't know their magnitudes. So if such a situation is there, and obviously the third vector, which is the VBA vector, here, that is completely known to us, that we agree that is completely known to us. But these two vectors, they are known in directions only. So this rule, it simply says that if this is the situation, then it is possible to find out the magnitudes of these two vectors, correct? So generally, if you remember, while we conduct this velocity analysis, right, so we have to keep in memory that if such a situation arises, right, then it is obvious, or it is easy to figure out the magnitudes of two vectors which are known in directions only, right? So now let's move ahead and let's see what is the next step. However, I would suggest that you keep this rule in your mind, right, because later on we are going to use this rule while drawing the vector diagram. So let's move to step 3. Now the step 3 is very obvious. In the third step, now we will start drawing the vector diagram, correct? Now there are certain sub steps, right, you have to keep in mind while drawing the vector diagram also, right? Now what are those sub steps while drawing the vector diagram, that I will tell you right now, right? So here the first step is obviously to draw the configuration diagram. Very important step. Always remember that the first step is always to draw the configuration diagram. Now for drawing the configuration diagram, you have to choose a convenient scale, right? And according to that convenient scale, you draw the configuration diagram first. Now why it is required to draw the configuration diagram first, that you will understand, right? Now let's start drawing the vector diagram. So obviously the first step in the vector diagram is to mark these points small a comma small d, right? Now what are these points, right? See, these points are basically your fixed points, right? That is point A, point D, right? So now you can mark these fixed points. So let's say, like, if there are n number of fixed points in the mechanism, you will denote all the fixed points with a single point in the vector diagram, right? So let us mark this fixed point as A comma D, right? So okay, so I have already marked it, so let me just erase this one, right? Now after marking this point A comma D somewhere in the space, now let's see what is the next step. So the next step is to draw the vector which is completely known, right? Now here the vector equation that becomes very useful to us, right? So you simply, on one side of your copy, you just write down the vector equation quickly. So this is VCD vector is equal to VBA vector plus VCB vector, correct? Now here, if you observe, we have already said that this vector is completely known in magnitude and direction, correct? So what we are going to do, we are going to draw this vector first. Now how to draw this vector, right? So we can say that obviously the vector VBA, it will be represented with AB vector in the vector diagram. That is very much clear, right? So the tail of this vector is this is small point A. So this small point A we have already marked in the vector diagram, right? Now the next step is to draw this point B. So what we are going to do, we will simply take a scale and then we will measure the length of this vector, or you can say mark the magnitude of this vector using the scale, and then we will keep this scale perpendicular to this side AB in the configuration diagram. Now that is the importance of drawing the configuration diagram first, because it will help you to figure out the direction of vectors, to draw the directions of vectors, right? So now we know that this VBA vector, it will be perpendicular to AB, and also we know that this VBA vector, it is going to point towards this side, the right side, correct? So now what we are going to do, so you keep your scale, right, perpendicular to this side AB, and then you simply drag this scale to this point A, right? So you drag this scale to this point A. Now once you have done that, after that you simply mark the length on the scale which is equal to the magnitude of this VBA vector, and you simply draw a line AB, something like this, right? So now your vector AB is complete. Now let's see what is the next step. So obviously the next step is to figure out the magnitudes of these two vectors, correct? So we know the direction, but the magnitudes are not known. So just now apply the rule that if we know the direction of two vectors, that is VCD vector and VCB vector, then it is possible to figure out their magnitudes also. So let's see how it is done, right, using the vector diagram. So here if you see in these two vectors, the common point is very important. The common point is this point C, right? So the common point is this point C. So let me write it down in this form also. So VCD vector in the vector diagram format, it will be DC vector, and VCB vector in the vector diagram format, it will be VC vector. Simple, right? Now here if you observe that the point C is the common point in these two vectors. So somehow in the vector diagram, if we figure out the location of this point C, then it is possible to find out the magnitudes of DC vector and VC vector. So let's see how to figure out the location of this point C, correct? So for that, first what we are going to do, we will simply take this point B in the vector diagram, right? So the point B we have already located in the vector diagram. Now through this point B, we are going to simply draw a line which is perpendicular to BC, correct? So again we will take our scale, right? We will keep our scale perpendicular to this side BC in the configuration diagram, and then we are going to simply drag this scale at point B in the vector diagram. Very simple. Now once we have done that, now what is our next step? Our next step is simply to draw a line, right, through this point B, right? So right now we are arbitrarily going to draw a line through this point B. Very simple, right? Now after this, right, the same operation we are going to repeat for this vector VCD vector, correct? Now again we will keep our scale perpendicular to this side CD, right, of the mechanism, right? So now we are going to keep our scale something like this, and again we know the location of point D in the vector diagram, right? So the location of point D in the vector diagram, that is already known to us. So what we are going to do, through this point D, we will simply draw a line perpendicular to which side? Perpendicular to this side DC, right? So let me draw this line. Now it is very obvious the intersection of these two lines, it should give us the point C, correct? So now the next step is simply to mark the intersection of these two lines as point C, right? So you can see here. Now after that, what you do, you simply join point A with point C and point B with point C, right? So let's draw these vectors. So now here the vector diagram, right, specifically for this point C is complete, correct? Now if the first part of the problem is solved, that means like we needed to calculate the velocity of, right, point C relative to A, correct? So that problem is solved here. Now how that is solved? It's very simple. Now once you join A with point C, so obviously the absolute velocity of point C is simply equal to what? It is simply equal to velocity of point C relative to A or velocity of point C relative to D, because ultimately we know that A and D both are representing the same point in the vector diagram, correct? So we will simply measure the length of this vector AC, right, and then we can simply write down that VCA vector is simply equal to AC vector. Now here you can see we are knowing the direction of this VCA vector also. So you can see here that this VCA vector, it is pointing towards the right side, correct? So this is how we can figure out the absolute velocity of point C using the vector diagram approach, correct? Now you have to just keep in mind that these two steps, they become very important while drawing the vector diagram. So let me take you back to what are those two steps. So like I will quickly summarize those two steps. So these two steps, they become very important, right? They help you to remember that which vectors you need to draw, right, and in what direction, in what sense you need to draw those vectors, correct? So the first step is to write down the vector equation, and the second step is to simply run a magnitude and direction analysis, right? So afterwards, let's move to the calculation of velocity of E relative to A. Now if you remember, right, when I was discussing the velocity analysis of a link, right, so if you remember, we had a link OA and then we took some point B on that link OA, and then we calculated the absolute velocity of this point B, correct? So the same rule we are going to apply here, right? So for calculating the velocity of E relative to A, so right now we already have this much vector diagram available with us, right? Now it's very easy, right? Here if you observe carefully, right, what we are going to do, we will simply mark a small point E, right? We are simply going to mark small point E on vector BC, right, on vector BC, such that, right, this small point E, it will divide this BC vector in the same ratio as capital E is dividing the length BC, correct? So this is very easy. Mark E on BC vector such that upon BC is equal to capital BE upon capital BC. Very, very easy, right? So let's do that. So here what we are going to do, see now, once this vector diagram is available with us, we know the magnitude of this BC vector, so we can measure this length BC vector. We can use that length here, and then we can substitute these two lengths, that is BE and BC, and then we can calculate this BE vector, right? So now you simply use this relation and mark this point E on BC. Now once you do that, let me just mark it quickly. Once you do that, now it's very obvious what you have to do to calculate the velocity of point E relative to A, or you can say the absolute velocity of point E. You simply join point small a with point E, right, and you just measure this length from the vector diagram. That will simply give you absolute velocity of point E, correct? So VEA vector is simply equal to what? BC vector, right? Now let's talk about this offset point F. That was our last parameter, last velocity vector which we want to calculate. Now let's see how to calculate the velocity of this offset. If you observe carefully that the vector equation for point F is simply given by VFB vector, obviously velocity of F relative to A, correct? So first we are saying velocity of F relative to A. So let me just quickly write down, that is VFA vector is simply equal to VFB vector, right? So both these two vectors are equal, right? Both are representing the absolute velocity of point F, because the points A and D, they are fixed. Now if you observe here that VFB plus VBA, that is VFA vector, it will be simply written down as VFP plus VBA vector, and then VFD vector, it will be simply written down as VFC vector plus VCD vector. This is very simple. You simply need to follow the order, that is the order F, B, A, right? And then you follow this order F, C, D, correct? Now once that is done, so let's see here. So VFB vector plus VBA vector is equal to, now similarly VFD vector you can write down VFC vector plus VCD vector, that is velocity of F relative to C, then velocity of C relative to D. Now once this is done, let's move ahead. Now you can simply rearrange the terms, or even if you don't want to rearrange the vectors, that's fine. Let's move ahead, right, and simply write down in this vector diagram format. So this is AB vector plus BF vector is equal to DC vector plus CF vector. Now you have to observe carefully one thing here, right? So what is that one thing? So now you can just simply refer to this vector diagram, and you obviously know that this vector is completely known to us, that is AB vector. So you can see this AB vector is completely known to us. Then another vector is BF vector. BF vector, now you can quickly run a magnitude direction analysis here. So we know the what? We know the direction. You can say that BF vector will be perpendicular to capital BF, right? But the magnitude is not known. Here now we know the magnitude and direction both of DC vector. So DC vector is already located in the vector diagram. This is your DC vector, right? Now coming to CF vector, again for CF vector we don't know the magnitude, but we know the direction. So we know that BF will be perpendicular to BF and CF will be perpendicular to CF, correct? Now how to figure out, right, the location of point F? Now why I am saying how to figure out the location of point F, again you can see here that these are two vectors which are known in directions only, but we don't know their magnitudes. So what I said, the rule says that if the direction of two vectors is known to us but their magnitudes are unknown, it is possible to calculate their magnitudes also. So that is the rule here, right? So now you can see here that in these two vectors, which point is common? this point F is common. So if we locate this F in the vector diagram, then we can easily figure out the magnitudes of BF vector and CF vector. Now you can also observe here that this point B, right, and the point C, the point B in BF vector and the point C in CF vector, that is already marked in the vector diagram, right? So now what should be our next step? Obviously the next step is simply, so let me go one by one. So the first step is simply to draw a line B, right? So draw a line through this point B, and this line should be perpendicular to BF, right? So obviously we, as I have already shown you, that we will keep the scale, we will drag the scale to point B, and then we will simply draw a line which is perpendicular to this dimension or this side BF, correct? So now here you can see that we will simply draw a line perpendicular to BF through point B. Now same thing we are going to repeat for the point C also. So through this point C, we are going to draw a line perpendicular to CF. So just remember, this line is perpendicular to BF and this line is perpendicular to CF. Now once you have done that, what should be our next step? Obviously the next step is to mark this intersection point. So this intersection point will be point F. Very easy, right? Now once you have marked that intersection point, now what is required to do? Now after that you simply join F with C, join F with B. Now what was asked to you? It was asked to you to calculate the absolute velocity of point F. So the absolute velocity of point F, it will be simply equal to VFA vector is equal to simply AF vector. So you can see here VFA vector is nothing, it is equal to AF vector. So you take a scale, you measure the length AF, correct? And then you simply say that this is the magnitude, and obviously the direction is also, right, here you can see from A towards F, correct? So the direction of this vector is basically pointing towards the right side, correct? Now I was telling you about a very important concept. So that concept is called as velocity image, right? Now if you observe carefully that this small triangle BCF, right, this is small triangle BCF, right, this is similar to triangle capital B, capital C, capital F, right? So let me just call this thing as that the triangle BCF in vector diagram, it will be similar to triangle BCF in the configuration diagram, right? So now this triangle BCF, it is referred to as velocity image of this triangle BCF in the configuration diagram. So always remember this thing, that the smaller triangle BCF in the vector diagram is referred to as velocity image of the, right, capital triangle BCF in the in the configuration diagram, correct? So now let me just summarize this. So another way, right, this was one of the way to locate the point F and to calculate the magnitudes of BF and CF vector, but there is another way also to do that. What is that way? That way is simply, once we know that these two triangles, they are similar, we can write down this equation as BC divided by BC is equal to BF vector divided by BF is equal to CF vector divided by CF. Now from here you just calculate the magnitudes of what? BF and CF vector. Why? Because we already know the magnitude of BC, right, BC vector from the vector diagram. The dimension of this side BC, that is also known to us. So obviously this value will be completely known to us, right? And from this value, what we can do, from this value we can obviously calculate BF and CF. So once you have calculated BF and CF, what you need to do, simply take a compass, right, keep your compass at point B, draw an arc somewhere here, right? And now again take a compass, right, take this radius CF, right, take this length CF, keep your compass here, draw another arc, and obviously you can say the intersection of these two arcs will be this point F, right? So that is another trick to solve for the velocity of an offset point, right? So just offset point, generally you follow these two rules, either you draw two perpendicular lines or you simply draw the velocity image, right? So velocity image is, let me just summarize it. So velocity of F can be calculated by rotating, see very carefully, that by rotating triangle BCF through 90 degree in the direction of rotation of length BC, correct? Now what does it indicate, right? See, we know that this side BC, right, it will be perpendicular to BC. this side BF in the vector diagram will be perpendicular to this BF, and the side CF in the vector diagram, it will be perpendicular to this capital CF in the configuration diagram. So obviously the sides BC, CF and BF in the vector diagram, they are all perpendicular to the sides BC, CF and BF in the configuration diagram, right? So we can simply say that now this triangle, that is triangle BCF in the vector diagram, it is simply obtained by rotating the triangle BCF of the configuration diagram. It's very simple, right? So that is what it is trying to convey. And also just remember this concept that here this smaller triangle, that is triangle BCF in the vector diagram, is called as velocity image of the triangle BCF in the configuration diagram, right? So the complete vector diagram which I am showing you here. Now let's move to the next part of this problem. So the next part of this problem is to simply calculate the angular velocity of link BC and CD. So now it's very obvious. So we know that angular velocity of link BC, it will be VCB vector equal to omega CB into BC. So we know that relative velocity of C with respect to B, that is VCB vector, is simply equal to what? Omega CB multiplied by BC, right? From here we know that omega CB, it will be simply equal to VCB vector divided by CB, right? Now this is the way to calculate the magnitude. Now how to figure out the direction? So let's see here, if you observe carefully, right, this velocity of C with respect to B, it is pointing towards upward direction. So from here you can conclude that C, it will tend to move upward with respect to B. So you can say here that this link BC F, it is going to rotate in a anti-clockwise fashion, correct? It's very obvious. With the direction of vectors you can actually figure out the direction of rotation of links also, right? Now let's move to angular velocity of link CD. So obviously for angular velocity of link CD you can apply the relation V equal to R omega. Very simple. So velocity of C relative to D, this will be equal to what? This will be equal to CD into omega CD. So I am just denoting the angular velocity using omega CD. So omega CD is equal to simply VCD divided by CD. So VCD divided by CD, right? And now let us figure out the direction. So it's very obvious. If you see the VCD vector direction, so you can see here that VCD vector direction, it is pointing towards this side, right? Towards the right side. So that means point C, it will have a tendency to move towards right side relative to point D, correct? So from here we can say that this link CD, it is going to rotate in a clockwise manner, correct? So here link CD rotates in a clockwise direction, correct? So this is the basic parameters which we actually need to find out while conducting the velocity analysis of a 4-bar mechanism. First, my idea was to convey you the process of graphical vector approach, correct? Now here, once you have understood the process, right, then we will go to the numerical problems, right? Then we will take up certain numerical values for all the parameters, and then we will see how can we actually calculate these velocity vectors, right? But right now my idea was to give you an understanding of the process first, right? So I hope the process is clear to all of you. So with this I would like to conclude this session and hope to see you in the next session. Thank you.